Okay, in this scenario, we have a child swinging on a swing set. They go really high up. They basically go to 90 degrees through the bottom, through the resting position or the equilibrium position. And Angela graphs that, of course, like any good physicist or physics student would. But she noticed something interesting, is that what you would expect in a simple harmonic motion situation, the dotted lines here, doesn't line up with what was actually noticed and measured in reality. And the honest reason for that is because the pendulum only experiences simple harmonic motion under small angles. So that's what's going on here. The angles are too large, and therefore it doesn't quite exhibit simple harmonic motion. That's the discrepancy there. You can just see these are not small angles. They took it to the pretty the extremes. So that is not a small angle going 90 degrees. Okay, so that's the first one. The next one, Angela is noticing that the child has a mass of 200 newtons, so she suggests that the tension on the chains is going to be 200 newtons as the angle is at 0. So in other words, at the very bottom of the swing. She says it's neither speeding up nor slowing down, so tension must balance. According to Newton's second law, seems to make sense, but the graph does not support that. So what's wrong with her reasoning? So here's what is going on. Yes, at theta 0, the child is not speeding up or slowing down. Okay, just so you know, but they are changing direction. So there is a change in velocity. That means that there is a acceleration, which means that, oh, hang on, this is just the part about what is correct. Yes, they're not speeding up. So there's nothing changing. It's the child's not gaining height, not slowing down. So those are all basically just different ways of saying the child is not speeding up or slowing down. But what is incorrect is, and this is what I was getting at a second ago, the child's not at equilibrium. There is an upward acceleration. And since there's an upward acceleration, there needs to be an upward force. So the force of tension is going to be greater than the force of gravity because the child is changing direction. So the graph, if you look at it, I'm not going to be scrolling back and forth because that'll make us all nauseous. But if you go back and look at it at theta 0, the time, when angle is 0, the time is about 1 second, and the tension is measured at 600 newtons. And this seems a little weird to say it, a little obvious, but say this kind of stuff. Why doesn't it support it? Well, 600 is greater than 200. Okay, come back when you see something like this and come back and state that. State the obvious mathematical truths here, okay? Don't just leave it at that. Like, okay, 600, you got to remind the person reading what you're writing what the claim is. And the claim is that the tension is 200 newtons. So say no. Remember when we said it was 200? Okay, well, look at 600 is greater than that. So it's not a bad idea to say stuff like that, just to make it very clear what the claim was and why it's incorrect. Explain why the tension is greater than 200. Cite specific physics principles. Make sure you do that. So the child is accelerating. In other words, the child is moving in a circle. There must be a net force toward the center of the circle. Okay, we learned that a while ago. So in the case of the child at the bottom, the center of the circle is upward. Since the tension points toward the center of the circle, the tension must be greater than the force of gravity, which points downward. This is the net force is greater than 0 because it's pointing upward. That's it. So just make sure you cite those physics principles.